Hi all. In last session, we talked about the convolution layer. We saw the concept of convolution layer related 4 steps, and we still to cover 2 steps remaining over here, and we'll continue with that. Just to summarize it, we have 8,000 images for training purpose, and my data set is available on my Google Drive. And this is mix of dogs and cats of various beautiful breeds. Our aim is to fit the model and train it using these training sets so that we can predict the input as and classify it as dog and or a cat with higher accuracy. The images are converted into 256 by 256 uniform size, and we also applied augmentation for each input images. The images are convoluted by applying feature detector. This reduces the dimensionality of the input image. And further, we apply activation function and we obtain stack of feature maps for the image. The same process is applied for each images of the training data set. Now, next step was pooling layer, where we applied pooling filter of size 2 cross 2 and obtain pooled feature map. So pooling step extract all important features of the feature stack obtained from the last step. Here we use max pooling filter. So we will cover pooling step code, and then we will go ahead with the flattening step. Now, flattening step is a process of generating input vector from pooled feature map. It creates vector of vectors containing feature map, and it is also known as a tensor. So this stack of vectors will be input to the neural network, and here we have feature map of size 64. Hence, as a result, we will have 64 vectors featuring each image. So our input layer of neural network will have 64 nodes to which we will pass on these 64 vectors. For your kind information, my data set is available at my Google Drive and execute this code. I'm using Colab. Now let us go ahead and learn how to work on fully connected layer, the neural network which will predict our input image as dog or cat. So here the code that we apply for our pooling step. Pooling step reduce size of convoluted images. It reduce size of feature map, and hence it reduce the number of nodes in our next step, which is flattening step. It also reduces the time complexity and high computations. We simply add max pooling 2D function where pool size is given as 2,2. So it's clear that we are using pool filter of size 2 cross 2, and since we are using the function max pooling 2D, our filter is max pool filter. Okay, now next step is flattening, and flattening process of like generating input vector from pool feature map. It create a vector of vectors containing feature map. This vector of vector is called as a tensor, and in our example, for each image of size 256 by 256, we created 64 stacks of feature map, which was then applied by activation function relu. All right. Now next is pooling step. This 64 feature map stack is applied over by max pool filter of size 2 cross 2. As a result, we obtain 64 stacks of pooled feature map, and each of the pooled feature is now converted into vector in this flattening step. So since we have 64 pooled stacks, we will obtain 64 vectors for each of them. So here the two-dimensional pooled features sets are transferred to a single dimensional vector. Each of this vector will be input to the input layer of neural network. We have vector of 64 vectors, so we also call it as a tensor. So for each vector we will have one input node, so our input layer will have 64 nodes. Okay, now flattening code is quite simple. we simply add this layer to our convolution object. The function name is flatten, and it generates tensor that means vector of vectors by converting all two-dimensional pooled feature maps into vector. Here is our final this is the code to add the to perform the flattening. We simply add flatten using the flatten function and obtain the flattening of the vectors. All right, so here is our final code, and final code is we'll have fully connection over here. So here is a final convolution neural net ready, and we can see all 4 steps in one step over here in a single image. And to summarize this, we have our input image, which we convolute in convolution layer using kernel of filter. We generated stack of feature map for every image. In our case, we generated 64 feature maps. Now, activation function is applied to this feature map stack, and hence convoluted feature map stacks are obtained. Next step is pooling layer. Here we apply pooling filter that extract important features from the feature map stack and build pooling stack. This important step, this is very important step, and as it reduces the dimension, finally this each of the pooled stack map is flattened into single dimensional vector using flatten function, and we have vector of single dimensional vectors, and it will act as an input to the input layer of neural network. Since in our problem we have defined 64 values for the feature map parameter, we obtain 64 single dimensional vectors, and this is how our input layer will have 64 nodes. Each of the node will receive input from corresponding vector obtained at the flattening step. Okay, and now question is how many layers we need at input. So hidden layer and output layer. So let us understand it. We don't need to define input layer, as it is obvious that our code we have 64 feature maps for each image that results into 64 vectors for each image at flattening step. Hence we will have 64 nodes at input layer. Now second question is about how many hidden layers we should have. And second obvious question is and apart from that, like another question is like how many nodes each hidden layer will have. As such, there is no fixed thumb rule for this purpose. Normally in simple artificial neural network problem, I follow thumb rule where I add input layer nodes and output layer nodes and take its average. But here the problem is very much different. We are working on image classification, and it is convolution based neural network, so our strategy will be different, very different. All right, so what we are doing is like here we already discussed okay, so here we define our hidden layer, and we already discussed that input layer is by default having 64 nodes due to our 64 feature map in our problem. Here we will have 2 layers in hidden layer. This is purely an intuitive decision. As a performance enhancement at later stage, we can increase number of hidden layers as well, and number of layers can be increased, and along with that we can also change with the nodes available into hidden layers. But the more hidden layer we have, obviously more computation burden will be on the network when we train it. So it will have very higher time complexity as well as computational burden on the processor. So here we will have 2 layers at hidden layer, and yes, each layer we will have 128 nodes. So higher the number of nodes, more features we can extract. But here we since we need to learn the concept to meet the constraint of the time complexity and computational burden, we go for 128 nodes at hidden layer. The code you can see here, first we add first hidden layer using add function. The add function is having dance function as parameter, and dance function has two arguments, output dim and activation function. Here the first hidden layer is having 128 nodes and it passes the output to the second hidden layer having 128 nodes. So our output dimension will be 128. We are using ReLU activation function here as it is most suitable for this particular problem. However, you can change the activation function and check for the performance at later stage. Now the second hidden layer again can be created using add function. Add function is having dance function as parameter that contain two arguments. First is output dim, just like the previous one, and okay, but here our output from this layer, the second hidden layer, will be our last, that is output layer. So output layer is having single node because this is classification problem and it is a binary type classification. So where the output will be dog or cat, that it means 0 or 1, hence the output dimension parameter will have value 1, and activation function for this purpose we will use sigmoid activation function. We are using sigmoid activation because we need binary output, binary classification. And here is our fully connected neural network. The task of creating and coding convolution neural network is over. Okay, so we have defined input layer, we have defined hidden layer, we have already defined the output layer. Okay, and now it's time to compile our CNN model. And to compile the model, we will use compile function with Adam optimizer. All right, and finally, we wish to measure the performance of our network. So here, using our performance matrix, we will specify to obtain accuracy and mean square error as a performance measure. So here is our compile code that compile our CNN. And all right, so great. Now our CNN is compiled and ready to train. All right, so using the compile function, we compiled it. We pass optimizer Adam. Our loss function is binary cross entropy we have used. There are different loss functions that you can use, which is part of your backpropagation. If you want to learn more about that, you can just go through my previous videos about backpropagation. I have already explained that in detail. And matrix, the performance measurement that we will use are accuracy and mean square error. So we define our output, the performance measure matrix as accuracy and MSE. Okay, great. So that's our CNN compiled. It is compiled and is done with that. Okay, and fine. Excellent. Our model is compiled and now it's ready to process the model. We will fit the model now, and then once the model is fit, we will test the model with the unknown data set of cats and dogs. We have in process to check the model accuracy. This we will do in our next part of the lecture, the final part, and see you soon with the next part of lecture. Till then, have a great day. Stay safe. Stay secure.